continue with the rational zero theorem. Let f be a polynomial function with a degree of 1 or higher. And let's go ahead and look at the form. So notice we have a polynomial. This is our standard definition, but you have to remember that a sub n cannot equal 0. And of course, a sub 0 cannot equal 0. And where each coefficient is an integer. So each coefficient has to be a whole number, positive or negative. And what we're going to do is we're going to do p divided by q, and I'll talk about what those letters mean. And in the lowest terms, it is going to be a rational coefficient. And I'm abbreviating coefficient of f. P is going to be the factor of a sub 0, which is the last term. And q must be a factor of a sub n, which is the leading coefficient. So the letters P and Q, I'm going to show you how I remember which one belongs to what. P is the constant. Q is part of the coefficient. It's the leading coefficient. That's just how I remember it. Q, I can spell, and it just sounds like co. It probably makes no sense to you, but it makes sense to me. And I always remember that Q is the coefficient, the leading coefficient. Okay, so here's what we're going to do. We're going to find all possible zeros for a polynomial. All real possible zeros for a polynomial, positive and negative at the same time. So what we're going to do is we're going to take P, which is negative 6. We're going to take Q, which is a positive 2, and we are going to list all of the factors, positive and negative. So factors that make 6 are 1, 2, 3, and 6. And I'm going to put a brace around both of those, positive and negative. For 2, remember 2's prime, so it's just 1 and 2. And then what we're going to do is we are going to divide, we're going to do P divided by Q. So we're going to take all these top numbers and divide them by all these bottom numbers. So what I'm going to do is I'm going to start with the first number here and just work my way. So 1 divided by 1, of course, is 1. 1 divided by 2 is a half. Now I'm going to go to the next number, which is at 2. 2 divided by 1 is 2. 2 divided by 2 is 1. I already wrote that, so I'm not writing it twice. Now I'm going to go to 3. 3 divided by 1 is 3. 3 divided by 2 is 3 halves. 6 divided by 1 is 6. 6 divided by 2 is 3, but I already wrote it right there, so I'm not going to write it twice. Same thing. The positive and the negative outcomes, quotients, those are all going to be possible rational zeros. So these are possible rational zeros. And remember, rational is real numbers. So these are all possibilities where this polynomial will actually cross the x-axis. Let's do it again. Let's take a look at example number 2. So P is a negative 3. So that's going to be the positive and negative of 1 and 3. Q, the leading coefficient, is a 2. So we're going to take the positive and negative factors of 2, which of course is just 1 and 2. So the possible real zeros for this polynomial is going to be 1 divided by 1, 1 divided by 2, 3 divided by 1, and 3 divided by 2. And the positive and the negative factors of those are possible zeros for that polynomial. So let's kind of wrap up what we just worked on. Remember the Descartes rule of signs? This is really like the nature. It's the nature of the roots. Positive, negative, or you can figure out how many complex there are. The rational zero theorem, these are real. And that's going to tell you all the possible real zeros for the function. Let's fill in some blanks. Descartes' rule of signs determines the possible number of positive and negative real, which are rational, roots. So Descartes just kind of tells you the possibilities. The rational zeros theorem, that tells you what those possibilities actually are. So the rational zero theorem determines the possible number of real zeros. This tells you the combos. This tells you what they actually could be.